Okay, problem 9.27, not chapter, yeah? Problem 9.27. An electronic instrument is to be isolated from a panel that vibrates at frequencies ranging from 25 Hz to 35 Hz. It is estimated that at least 80% vibration isolation must be achieved. Okay, that 80% is actually isolation efficiency, all right? Isolation efficiency or isolator efficiency achieved to prevent damage to the instrument. If the instrument weighs 85 Newton, find the necessary static deflection of the isolator. Okay, first of all, look at this side here. Okay, look at this side here first. All right, first of all, as you can see here, this is a formula for isolator efficiency. All right, given, you can find this PDF also in the Moodle. Okay, it is accessible through the Moodle. Okay, given here three types. This is specifically for vibration isolation. First type is the vibratory force, where the machine is moving and the base is rigid, fixed. It is not moving. Second is isolation of vibratory motion, where the motion of the base, right? Motion of the base. Base is having a motion now. Just now is rigid foundation. The base is fixed. All right. So if basically, as you can see, the formula, everything is actually quite the same. All right. If it is vibratory force, where your machine is moving, the foundation or the base is rigid, fixed, so it is labeled as TR, where the formula of TR is Ft over F naught. All right. And if as you can see, everything is the same. Okay, I'm going to remind you guys once more, everything is the same. But for vibratory motion, where the base is moving, it is labeled as TD. Alright, TD, where TD equals to X over Y. And lastly, for rotating unbalance, for isolator, it is labeled as TR. T with a big R. Okay, where TR is equals to Ft over ME omega square. Alright, so basically it is actually the same, where F naught also equals to ME omega square. As you can see here, Ft over F naught, Ft over F naught, but your F naught now is ME omega square. And your isolation efficiency is IE, and this is the formula for isolation efficiency. Alright, so next. Alright, so as you can see here, one thing. Alright, the R for vibration isolation, the R needs to be more than square root of 2. So using the formula for isolation efficiency just now, IE equals to 1 minus TR times 100%. But now we are doing for vibratory motion, right? Where the base is in motion, not the machine. Alright? Okay, the panel now vibrates, not the electronic instrument. So we labeled it as, for vibratory motion where the base is moving, TD. Alright, so TD. Okay, instead of TR. This one I just copied from the PDF just now. So, where your isolation efficiency is given 80%. So you just have to calculate this. Okay, so times becomes divide 80% divided by 10%. Okay, you get basically your TD, you'll get your answer to be 0.2. Okay, given also the weight is 85 Newton. So from 85 Newton, you can use the formula where weight equals to mg, right? Okay, W equals to mg. So from there, if you want to find your W equals to mg, if you want to find your m, so basically m equals to weight divided by gravity. Okay, so that's how I get the mass is 8.6646 kilogram, where your gravity is 9.81. And the frequency is given in for two types of frequencies now, okay, from 25, ranging from 25 to 35 Hertz. So you can change both using omega equals to 2 pi f. So for that, you'll get your omega, if f is 25, your omega is 50 pi. If your f is 35 Hertz, your omega is 70 pi. Okay, they didn't mention anything about damping or damper inside this question. So we can assume that C is 0, automatically zeta also 0. Damping ratio also 0. So using the formula of TD here, alright, if your zeta is 0, you can cancel that out. So in the end, you'll be left with 1 over 1 minus r square. Since this whole thing here is inside of a square root, so once you take out the square root, alright, because square root 1 equals to 1. Okay, square root of square, they'll cancel out each other. So, but since they are inside a square root, you must put modulus here, because nothing inside a square root can be negative. Okay? Or else it will be imaginary. So, I bring 1 to the other side. Okay, 1 divided by 0.2, you get 5. So you'll be left with this. But remember, modulus, if you bring modulus to the other side, because we want to solve for the r, it will become plus minus for modulus. Okay. So from there, I want to find the r. 1, bring it to the other side, becomes negative 1. So I can separate this into two equations where positive 5, another one is negative 5. Alright, so for this one, I'll get negative 4, which is invalid. So another one, I'll get positive 6 square root of positive 6. So this is our r. Okay, and our r now is more than square root 2, which is correct. So now let's go, since we have two frequencies, so we can find the static deflection for both frequencies. Okay, one at 25 hertz, another one at 35 hertz. So since we already have our r, we know that our r equals to omega over omega n. Alright, so basically same step for both. Okay, so I'm just going to show both at the same time. Alright, so now, since we know our omega, right, our omega is 50 pi until 70 pi, so we are doing for both now. So that's why I substitute 50 pi and 70 pi over omega n, okay, equals to r, which our r that we get down here on the right side of the PDF. Okay, so we want to find omega n. So bring omega, which is 50 pi, and the 70 pi to the other side, divides with square root of 6. You'll get your omega n at respective frequencies. So now, we already have our omega n. We want to find the k. Alright, we want to find the k. So, we want to find the k. So, bring square root to the other side, becomes square, omega n square. And then divided by m, bring it to the other side, becomes multiply. So m multiplied with omega n square equals to k. Alright, same for both. We already have our m here. Alright, which is equals to 8.6646. Omega n at respective frequencies. Plug it in. And you get the value of k at each frequencies. The third step will be to find the static deflection. We know that the formula for static deflection is force divided by k. Alright, force F equals to kx, right? X is the deflection. Alright, so deflection equals to force over k. But our force, the only force that we have here is now the weight. The weight is 85 Newton, right? So weight equals to mg. Same thing lah. Weight equals to 85 Newton. Force over k, the k at respective frequencies. Use that. So 85 minus the k at respective frequencies will get our static deflection at both frequencies. Okay, one is 0.024 meter, another one is 0.012 meter. Okay, the static deflection of the isolator. Okay, now since we have two values of static deflection, we want to find which one is the correct one. Alright, we want to find which one is the correct one. So this is why we do the fourth and the fifth step for both frequencies. Okay, so let's take a look here. So we know that the static deflection is, the damping ratio is 0. So since both is 0, we'll get this right just now, this equation. Once both damping ratio is 0, we get 1 over 1 minus r square modulus. But now, since we want to check which one is having, if we use the frequencies both, okay, we cross use the frequencies, we can find which isolator will be having a better efficiency than the other. Okay, so let's say for frequency 25 hertz, the omega n is 64, right? So that's why use 64 here. Okay, we know that this formula here is 1 minus 1 minus 1 over 1 minus r. So this is r squared, this is r squared, all right? The omega n for at this on the left side is 64, so the omega n is fixed according to the respective frequencies. Omega n 89, see I use 89 also. The formula for r is omega over omega n. Initially, the omega for this frequency is 50 pi and the omega n is 64. But then 50 pi, I use it here, and 70 pi for this frequency, I use it here. Okay, I just maintain the omega n. For each side, the omega n maintain, r equals to omega over omega n. Sorry, the omega n maintain, just that I cross use the omega. Okay, just want to find at which omega it will be a better frequency. Okay, which one will be having a better frequency at each omega if I cross use the frequencies. So from there, I'll get my TD. Okay, this is TD for frequency 25 hertz. This is a TD for 35 hertz. All right. So the last step will be to find the isolation efficiency. Okay, we want to find at both frequencies, if we swap the frequencies, which one will be having a better efficiency. So the formula is 1, this is the formula, use this formula, 1 minus TD, okay, not TR, this is vibratory motion, TD. So 1 minus TD times 100%. So 1 minus TD times 100%, I'll get 90.71%. For this part here, if I minus the TD, 1 minus TD times 100%, I'll get 51%. Okay. Initially given, it is estimated that at least 80% must be achieved. Since this part here, we get 51%, which is less than 80%, we reject that part. Okay? Meaning the static deflection is not 0.012. Since 90.71 is more than 80%, which is actually better than 80%, that's why we use our static deflection to be 0.024. Alright? We don't use this. We use the static deflection at 25 hertz. Okay, and that is all for 9.27.